Hello. Welcome to this video segment in which I'm going to take the idea of an electric field equation and a little step further. In the first unit, I really had you just recognize the expressions for the electric fields due to different charge arrangements, the simplest of which was a point charge and then maybe a couple or a few point charges like a dipole. And then we went into what we call continuous distributions of charge, things like lines and sheets and rings and disks. And rather than just recognizing those, I want you to at least understand how those equations are derived. And it's spelled out in most good textbooks, but it's not the easiest thing to follow if you're just new into calculus. And so I'm going to take you through each step, and I just want you to be able to recognize what happens in each step. I think in my assessments, I'm not going to expect you to just start from scratch and derive the equation yourself. That might be a bit much for a lot of you who are just new into calculus. So if you can at least recognize what happens in each step of the derivation, I think that would be probably at a good level for you. So here's a situation that we're going to deal with. This is right out of our Dr. Knight textbook. You take a bunch of charge and you put it on a long line, evenly distributed, and that's a charge of Q over a length L. And so when we do this with continuous charge distributions, we now say that there's a charge density on the object, and that is Q divided by L. And our question is going to be, at this point out here, a distance d away, how strong is the electric field? So if we can get an expression for that field in terms of d, then we're going to see that dependence. And we did this for very long lines of charge when we did the last unit. We saw that there was an inverse dependence. And with a point charge, we remember there's an inverse square dependence. And with sheets of charge, there was actually no dependence on distance. So we're going to see how we arrive at that. And this is going to be a little different because it's just a short length of L, not an infinitely long length. So here's the diagram that is included in the textbook, and just going over a couple of important parts of this. We've taken this line and divided it into a countable number of charges, and we could number them, 1 to 12 or whatever you have, 1 to 50. But we usually just say, well, let's just treat part of this charge, a little segment of charge, and in this case, he's chosen this segment up here. That's totally random. And said, let's find just the little part of the field due to that. And if we can do that, then we can sum up all the other little pieces of charge, their contribution, and get the net field. So he's going to name this segment I, just sort of a random name there. And notice that segment I is creating an electric field that's pointed down and to the right. But realize that at some point you're going to have to deal with the segment on the other end of the line that's the same distance away, and it's going to create an electric field that's just the same size but a little bit upward. And do you see how the vertical components are going to cancel out there, which means we only have to deal with the x components. So that'll be one of the early steps in our derivation. We have, let's see, we have the charge density described here. I mentioned that before. So each of these little segments of charge is just the charge density lambda times the little length of that segment. That would be called delta y. And so I think what I'm going to do here is show you the derivation for the countable number of charges, like we drew on the figure, but also next to it, show you what we do if we want to do this the calculus-y way, and that is to treat it as an infinite number of charges. So the first step in the process is just to say, well, how big is the electric field due to just that little segment there? I might call it like a fieldlet, if you will. We're just going to add up all the fieldlets later to get the total. So now I made up that word fieldlet, so don't go using that too often. So we call a little fieldlet delta E. And that delta just means a small little piece. Kind of like delta y over delta x when you did slope. It's just a little part of the rise and a little part of the run. That's used a lot when you understand calculus. And each of those then will create a field of k times the amount of charge, that's a delta q, on that little segment. I'll just label it that segment. And then the square of the distance away. Now we're using a point charge equation because that little piece of charge is treated as a point charge. Now in calculus, you don't use deltas, you use the other version of a delta, which is a d, but everything else is pretty much the same kind of expression. So it's k and then dq and then r squared as well. Now I think in order to save some space and some writing, I'm going to deal with that whole symmetry thing right now and say we only need the horizontal components because the x components, or the y components rather, will cancel out. So how do we do that? Well, we just got to multiply by the cosine of that angle that the vector is making from segment I. So I'll put that over here as well. And how big is that angle? Well, here's the angle. We need the cosine of that, which is the adjacent side, that's d, divided by the hypotenuse of that, that's that. Now notice I'm working on this side, because the angle theta here is also the angle theta here for that little segment. So I'm going to put d over r and rewrite my expression. Everything's pretty much going to be the same here, except for that last little bit. And there's r. So we'll write d over r. Again, that r is going to depend on which segment. D is not going to depend on which segment, notice, because it's always the same. And I guess the same thing would happen over here. Trying to keep things real parallel for you. That's d over r. Okay, so what are we going to do next? Well, I think what I'm going to do is replace the r with what it's equivalent to. Notice r is the actual distance that that little piece of charge is to the point where we want to find the field. And it's a hypotenuse of a right triangle where we have one side that's y, the distance that little segment is from the center of the line, and then here's d again. So if we replace r with that, then we're just going to rewrite it again. K delta q for little segment I, and then r squared. Now r squared is equal to the opposite side squared plus the adjacent side squared, so I will just write it this way. D squared plus y. Now y again is going to depend on which segment. So there is r squared. Now if you don't mind, just to keep things a little more brief, I'm going to put d over r in a slightly different form. Here's going to be d up here, but r is just another one of these. So instead of having 2, we have 3. So I'm going to write it as 3 halves. Okay. Now again, r is the square root of d squared plus y squared. We had 2 of them here, which is why I left the square root off. And we have 1 of them here, so that's how you write the cube of a square root. And of course over here, we still have the same kind of thing. K dq. Now we have a d. I'm a little nervous about using d. I kind of wish he hadn't chosen that symbol. We already incorporated into our symbols in calculus, and I think it's just inviting trouble. But I don't really have the option of changing it very easily, so I'm just going to let it go. I am going to kind of keep it separated like that, so if somebody doesn't think that that d and that d are somehow the same. All right, and what are we going to do next? Well, we're going to say if that's the little fieldlet from just that one little charge, how would we get the contribution of all of them put together? Well, that's just summing up. So when you sum up a countable numbers of things, you just sum up all of the little contributions. So this is the sum of k delta q for segment I. And we got our d out here. And then we've got d squared plus y for that segment squared to the 3 halves power. Or over here, in calculus terms, We don't write a summation that way. We write a kind of a funny looking Superman S, and that will give us our total field. So we sum together an infinite number of things, and we make it look like that. So we've got, I think what I'm going to do now is maybe change some places. I'm going to bring the D over here. I'm going to put the DQ out here. That's where most calculus people are used to seeing it, kind of set off by itself. It doesn't really change what you're doing at all. All right, so that's what we got in both forms now. Okay, here comes an important substitution. And this is probably the one thing that I don't think is the easiest thing to remember. But remember that the little delta Q is related to the charge density and to the little length of the segment. We call that delta Y. Again, when you split a big number of things into a countable number of things, each one is called a delta. So I'm going to make that replacement because my expression has a delta Q in it. Okay, so here's what I'm going to do. I'm going to say delta Q is just lambda times delta Y. And that's for any segment and all. I'm going to put it in for little segment I here, since that's the one we're treating. And what are we going to do over here? We're going to do the same thing without deltas. We're going to say dq is lambda dy. And everything else is, again, going to be pretty much identical. You're going to see how this suddenly starts to look like something that maybe you've done before in calculus if you've solved integrals like this. So rewriting again, we're looking for the total x component of that is the sum. Oh, that's a nasty looking summation. Do that a little better. There we go. The sum of, and we've got k. I think maybe I'll pull this d over here. I did it on the other side, and I can kind of write my lambda. Remember, here's my substitution. Instead of delta q, I'm writing lambda delta y for that little segment. And then everything in the denominator still the same. Anything dependent on those little segments, I'm putting a little I on it. And I think I'm also going to do this now. You say, well, how many things do you need to sum together? Well, it kind of depends on how many little pieces you broke it into, right? So I is just going to be a number you're going to count from 1 up to whatever that number is. That's just a little notation we use with summations. Do something a little different over here when we do calculus. With calculus, you don't count up a countable number of things. You have limits on what you're summing. And so I'll incorporate that here in the next step too. So how am I going to write this? Well, my x components add up to the sum of k and d. Now here's where I'm going to make the replacement for dq. It's going to be lambda dy. Again, kind of setting dy off by itself, just from familiarity for a lot of you. 3/2. Now I said it's going to start to look recognizable for you because you're used to seeing your variable out here next to the little d. We had a dq, but what was weird was we never had a q anywhere in this expression. So you would say, well, how do I even do that antiderivative, that integral? Well, now you can kind of recognize it because here is your variable. Everything else in there, the d, the lambda, the k, those are all just constants. So those just kind of go along for the ride, I usually like to think of it. And I said I would put in the limits here. The limits when we do the integral is like how big and how little can your variable be? Well, now that my variable is y, if we look back up here, how big and how little are y going to be? On this side, y is going to go up to half of the length. And this side, we put in a limit of negative half of the length. So let me incorporate those, and then I really do believe you've got a situation where you can probably perform this if you've done a little integration already. Now, I'll be honest with you, I'm not the world's expert at calculus just because it's been so long since I've done it. So what I'm likely to do is I'm going to look this up on a table somewhere. I'm going to put it into Google or Wolfram Alpha or something like that. Now our textbook has a nice table and you can actually find the antiderivative of something that looks just like this. But honestly, at this point, we're done with the physics. This is now a math problem. How do you simplify that and get a nice expression? And that part's done for you, I think, pretty clearly in the book by using the table in the appendix. I'm going to stop here. I think this is enough for you to kind of see the important steps, those things that would be challenging probably for you to have caught on your own. So this is just the first of the videos. I'm going to do another one with a rounded shape, a semicircle of charge, because it's similar, but it's got enough differences I think it's worth looking at. And you can find other things as well. I'm going to let you examine the ring and the disc kind of by yourself. See how you handle those, and then hopefully if you kind of understand each step there, you're able to answer a few important questions if I give you one on a quiz or a test. So replay this as necessary. I know it was kind of long, not really in the mood to replay it, but some of it that you might miss, I want to make sure that you go back and revisit it a little bit. So good luck with this, and if you need any help, just come and see me and we'll talk through it.